So checking A by letters. Math. Then the next one, I can't remember the exact date, is like late January. And then the one after that is like right before spring break, like late March. So those are our three check-ins. I'm going to review a little bit. Each check-in works the same. There are 5 topics. There are 25 questions, at least for 8th grade math. They work the same that way. Topic has 5 questions. 5 times 5, that's where the 25 comes from. For this check-in, just going in order with how we did it this year, we got rational and irrational numbers, and we got laws of exponents. Both of those were from our first unit this year. So been a little bit since we did those. Then we got transformations. That was our second unit. Equations and inequalities. Some of those are active, some of those are inactive. So you have to. That was unit 3. And then we even have identifying functions, which was what was on your test you took yesterday. All right, so that one's a little bit fresher. Hopefully remember that. It have everything from your test yesterday, just has identifying functions. So the good part with that is we don't have to worry about the linear or nonlinear parts of it. It's just whether or not something's a function. Any questions on it? I cannot remember for certain because it's different for each check-in, active and how many are inactive. For the first one, I am pretty certain it is more on the active and probably something like 8 inactive and 17 active. But that's okay, so I'm on that. So let's need to identify which one of those is irrational. So, who thinks they can tell me the irrational number? Cam? Nope. Alea? Hmm? All right, so the way this works with rational and irrational numbers, decimals that are repeating, the line on the top means it's repeating, are rational. Decimals that are terminating, that means it's a decimal that just stops, those are rational. For a decimal to be irrational, it has to be something that keeps going without repeating. Usually you see the 3 dots at the end of it. Okay? So irrational would mean the 3 dots at the end. The line over the top, that's going to be rational. That can be written as a fraction. Rational numbers can be written as fractions. So a fraction is always going to be rational. Okay? As long as it doesn't have like letters or pi symbols on it. Square roots that we know are rational. Square roots that we don't know are irrational. Okay? A lot of y'all look at this one and think you don't know that because of the decimal, or the decimal messes you up. When it has a decimal, just ignore the decimal part of it. And basically what we got is the square root of 64. Y'all, what number times itself is 64? 8. 0.64 would be 0.08, actually. Or sorry, no, you're right. 0.8, sorry, my fault. Okay? Everybody kind of follow on that? Then, square root of 18, we don't know square root of 18. There's no number times itself that makes 18. 4 times 4 is 16. 5 times 5 is 25. So it's somewhere between 4 and 5, but we don't have an exact number that makes it irrational. The other thing that can make something, like let's say a fraction, irrational is if we have a pi symbol on it. Okay? Pi would make a fraction irrational because it will be a decimal that keeps going without repeating. Now, sometimes they'll get tricky on stuff. Your test had one where they tried to get a little tricky, and they had a pi symbol on the top and the bottom. If you got pi on top and bottom, it's still going to be rational because those pi symbols can cancel out. Okay? All right, I need an answer for this one without an exponent. Let's see if we remember how to do these. Yeah, this would be inactive stuff, so you'd probably have to do it without Desmos. All right, so pay attention. When we have negative exponents, you flip the exponent, make it positive. So instead of being up here, it's going to go to the bottom. So I'm going to have the 2 squared to the 3rd power on top. My negative exponent is going to go to a denominator. It's going to become positive. Okay? So negative exponents, you flip them, make them positive. Then, okay? What we're looking for is where there's more. So are there more on the top or more on the bottom? Top, how many more? 4. So that's going to give us to the 4th power. If there was more on the bottom, then we would have 1 over that. Since there's more on the top, it's going to be like a whole number. And then we just multiply it out. This is 2 to the 4th power. So that's 2 times 2 times 2. 2 times 2 is 4. Times 2 is 8. Times 2, 16. Any questions on that? 256. you did 2 to the 5th power or 2 to the 6th power, one of those, and then you multiplied it by 4 with the negative exponent, you end up dividing by 4. So you would have 64 divided by 4, which would be 16 if you multiplied it out. Any questions? Yeah. How'd I get this? When you have a negative exponent, it flips it. So what we have to start with basically is like everything's on top over 1. It's like they're whole numbers. Okay, so whenever we got a negative exponent, the negative exponent moves to the bottom. If the negative exponent happened to be on the bottom, it would move to the top. Okay? Just numbers by themselves, it's like they're over 1 in terms of thinking like flipping it, okay? There, negative 1's correct. So look, 3 units to the left. We're looking for K prime, so we're going to take K and move 3 left. If I move 3 left, I go 1, 2, 3. That's putting me right here. Then it says 4 units down. So if I go 4 units down, I start here, go 1, 2, 3, 4. That's putting me right here. That's my new order pair I need. The X value there, well, I covered it, but the X value is -2. Y value -1. So -2, -1. Any questions on that? When you have translations, left and right are your X values, up and down are your Y values. Right means you add. Up means you add to Y. Down means you subtract. So if we looked at K to start with, K was at the point 1, 3. 3 units left. Left is the X value. And it means we subtract. Subtraction. So if I subtract 3, 1 minus 3, that gives me -2. My Y value was positive. So we subtract 4. 3 minus 4 gives us -1. Most of what you see probably will have like a graph or picture to it, but not necessarily all of it. All right, find an answer for this equation. You can use Desmos. I feel like most of these, or more of them, are active than inactive, so. Brian, what you doing? If you put that in Desmos, this goes on one line, this goes on another line, and it will graph for you. If you have parallel lines are no solution on Desmos. Lines on top of each other are infinite solutions. Where they cross, that's when we have one solution. So, other thing you could do, if I distribute 3 times 4x is 12x, 3 times 5 is 15. 2 times 6 is 12x. 2 times a minus 7 makes a minus 14. After I distribute, my coefficients are, but I have different constants. If I have the same coefficients, that's no solution. Infinite solutions would mean everything was the same solution. No solution stuff. You had one like that on your test where you had to drag and drop them to like kind of sort them. That's a pretty common way to show those or have those done in terms like EOG or check-in possible. So you could easily have like 3 equations and have to put them in the correct spots, whether they're no solution, infinite solutions, or one solution. Okay. Any questions on that one? All right, so this is going to be a little hard to see from your seats, probably. To fit multiple tables up there, they got to stay tiny. So this is what we did, just on our test. Shania, what you got? A is correct. Why is it A, though? Yeah, A is the only one that has repeating X value. So on A, we got any questions on that one? I mean, basically, just one question for each, but like on your check-in, okay?